Alright, so let's talk about how many different 5-card hands can be made from a standard deck of 52 cards. So, 5-card hand means you're holding 5 cards in your hand, right? You pick out of 52 cards and you hold 5 of them. So let's say that these slots represent the 5 cards that you're holding. So, how many choices do you have for the first card? Well, you're thinking probability. Like, how many total cards do we have to choose from right now? How many cards do we have to choose from here? Good. 49 and 48, right? So, we'd have to multiply these together to get the total. But when you get this answer, it's not quite the answer. There's one more thing we got to do. So it's going to be 52 times 51 times 50 times 49 times 48. And this amount comes out to be 311,875,200. That's 311,875,200. Now, let's talk about why this isn't quite the answer, and we need to do one more thing. So, this is how many 5-card hand combinations we have. So, if this is my hand, let's pretend this is my hand, King, Queen, Jack, 10, Ace, okay? Does it matter which direction I'm holding this hand in if I switch around the order of the cards? Do I still have the same hand of cards? Yes. So the problem with this number is we counted it as if we're counting each individual order as well. Do you already see what I'm saying? So we're also counting if we move this hand in a different order. So in order to counteract that, we need to divide this number by something. We need to divide this number by the number of arrangements. So we need to talk about the number of arrangements of 5 cards.
So why do you count down from 52?
Because if you have 52 cards in a deck, you take away one of them for the first spot, you only have 51 to choose from. Now you only have 50 left in the deck. Now you only have 49 left in the deck.
So you're just taking one card away?
Yeah, because you're picking it up. So now the deck only has 48 left, or whatever it has left at that point. Every time I take a card out, the deck has less cards to choose from.
So in those 5 are going to be your first 5 hand, like your first card hand, like those first 5? Okay.
Yes, we're assuming we're picking out of a 52 because they told us to.
Okay.
So now we're going to talk about the number of arrangements. So if you have 5 cards in your hand, there's different ways we can arrange the cards, right? We can switch them around the order in our hands. We have to figure that out. So if we have 5 cards, the first slot has how many cards to choose from? 5. We have 5 cards to choose from in that first slot. We've already placed 1 card, so now how many cards do we have left in this slot? And how many do we have left here? 2 and then 1. This is the number of ways you can arrange a hand of 5 cards in your hand. And that actually comes out to be 120. So, to put it simply, if you are holding 5 cards in your hand, there are 120 ways you can arrange that hand in your hand. Did you ever think it was that many? No. Yes, there's 120 ways you can arrange it. So, we're going to talk about how this applies to our problem. So, this number right here is how many total ways that we can arrange, or we can pick 52 cards and then arrange them. All the arrangements are counted. So we have to take this amount and we have to divide it by what? 120. Because that will take away the double counts of all the arrangements that we're doing. Because like I said, if I have a hand of 10, Jack, Queen, King, Ace, I don't care what the arrangement is. It's still, whatever the hand is. So that amount comes out to be 2 2598960, which is 2,598,960. So for this reason, I want to talk a little bit about what this all means, how we just calculated two different things. All right. So one of these is what we call a permutation, and one of these is what we call a combination. So a combination is basically when we select a group of things, we don't care, right? When you guys group up into group work, and I tell you to put your name on the slide, do I care what order you put your names in? No, because you're the same group, right? That would be a combination. A permutation is when you take those elements of the group and you order them, also you count the orders of different ways you can arrange them. So permutations is always going to be a larger number of things because it's basically taking it and counting each separate order as a new count. Does that make sense? So that's the difference between a permutation and a combination, and we'll talk more about that in the lesson. Alright, so today we're going to be talking about 8.5, which is counting permutations and combinations. So this is a topic in math. You hear the word counting, you're thinking simple elementary school counting. This is actually, can take up whole courses in college math studies, okay? This is a whole branch of math that we talk about counting principle. So permutations and combinations are a way that we use to count things, and they mean different things. So we'll talk about the difference. So the fundamental counting principle is a rule used to count the number of possible outcomes in a situation. If you have one event with A possible outcomes and another event with B possible outcomes, the total outcome is the product of possible outcomes A times B. So the fundamental counting principle, we take the event 1 possible outcomes times the event 2 possible outcomes, and that product will give us the total number of outcomes. This principle can be extended to more than 2 events, so if you have 3 events or 4 events, you can also multiply those together as well. So let's look at some simple examples to start getting the concept of the counting principle. So it says here, you go to Jersey Mike's and order a combo meal consisting of a sandwich, chips, and a drink. There are 10 sandwich types, 4 chip varieties, and 6 drink options. How many different variations of the combo meals could you order? So, I like to draw slots for a lot of these problems just to kind of get a conceptual understanding. So my first slot is going to represent sandwiches, next one is going to be chips, and the next one will be drinks. So how many sandwich choices do you have?
2.
Good. How many chip choices do you have?
4.
Good. And how many drink choices? So if we multiply these together, this will give us the total number of variations we have, right?
Mm-hmm.
So this will be 240 variations. So what that means is you can go into this store and order 240 times and not order the same repeat thing. You always have one thing changing. Does that make sense to everybody what I'm saying by that? Okay. So do I have any questions about example 1?
So you wouldn't have to divide it?
No, in this case we don't have to divide it because each one of these things represents something different. Good question. So in this case, since they all represent something different, we don't have to divide because the order doesn't matter here automatically because they all mean something different. So Colorado is redesigning its license plate to consist of 5 alphanumeric characters, with the first 3 characters being letters, the 4th character being a number, and the last character being either letters or numbers. Will there be enough tags for Colorado's 1.7 million registered vehicles? So, the license plate has 5 alphanumeric digits. So we're going to draw a slot for each of those digits. So alphanumeric just means a combination of numbers and letters. So if the first 3 characters are letters, how many letters are there in the alphabet?
Like 26 or something.
Good. So for the first slot, we have 26 choices, right? We have 26 choices of how many letters we can choose from. Now, does it say anything about not repeating letters? No, so we assume that if they don't mention we can't repeat letters, we assume we can. So how many choices do I have for the the second slot?
26.
I still have 26 choices. If I chose A here, I can choose it again here. It doesn't say we can't. And then for the third, I have how many choices still?
26.
Good. So the first 3 characters are letters, which we just filled in. Now, the fourth character is a number. And when they say number, when we think of a digit, it's got to be a single digit number. How many single digit numbers are there?
9.
Not 9, almost. 10, because you have to count what?
0.
0. So there's 10. And then the last character can be either a number or a letter. So how many choices do we have for numbers and letters? Good. So we would multiply these together. That's not right. I was like, that's not what I got earlier. That's better. So this comes out to be 6, 3, 2, 7, 3, 6, 0. I put the commas in to read it. I always put commas in to read my numbers. So 6,327,360 unique license plates. Okay. These are unique plates. So we don't have to divide by anything here because we care about order, right? Because two license plates can have all the same digits but be in different order and be a different plate, right? So order does matter here, so we don't have to divide by that because we do care about order. When we do, we don't have to divide. Now, does that mean we'll have enough tags? Yes, we'll definitely have about 6 times, maybe, well, not quite 6, but like 4 times more than we need. So this is a bit of a fun fact and things that I actually started to notice this, which actually kind of made me study combinatorics. If you go to states that have a really small population, or you see license plates from states that do, if you like road trip, like Wyoming and Montana, you'll notice they actually have really simple license plates because they don't have to have as many combinations, right? Why wouldn't they need as many? Low population. So in Florida, for example, 3rd biggest population in the country, I think, maybe 4th, they have a lot of people, so we have to have a lot of plate combinations. So, fun fact.
So if you can repeat the letter, would it go from 26 to 25, 24?
Exactly. Correct. Good. We're going to do an example like that as well. A similar one, but good question. So, how many number patterns can we have for a 3-digit lock? And it says it's okay to repeat numbers. So 3-digit lock, how many choices do we have for the first digit? 10. How many choices for the second? And for the third? 10. We multiply these together because we need them all to happen simultaneously. And that's 1,000 patterns. Now, once again, order does matter here. Because if you have a locker combo and it's 256, is 652 going to open it? No, see how order matters? Which means it's a permutation. We don't need to divide by anything. Any questions about that?
Wait, so all of these permutations then, since we didn't have to divide by anything?
So far, yes. Except for the first one, which is a different kind of question because each one of those categories represented something different, which is why we didn't. So the next one here is non-repeating numbers. How many unique number patterns can we have with a 3-digit lock? So basically it's saying that none of the numbers can repeat. Like on the last one we could have had 222, but this one we can't.
So it would be 1098?
Correct, 1098. So you have 10 choices for the first, 9 choices for the second, and 8 choices for the third, which comes out to be 720 patterns. So obviously we have less patterns when we can't repeat digits. We removed all the repeating ones by doing that. Does that make sense? Okay. So yeah, like I said, lock patterns, the order does matter. So now we're going to talk about combination versus permutation. We're going to talk through some logic behind this, some concept. So here's something that can be a little bit confusing in math. When we talk about things in the real world, we use words very fluidly in English that we wouldn't use that way in math. So in English, we use the word combination really loosely, without considering how important the order really is. A fruit salad, you might say, is a combination of whatever fruits you're adding to it. So say you have a fruit salad and you add apples, grapes, and bananas. You might call this a combination, but it's actually not a combination, it's a what?
Permutation.
It's a permutation because, well, wait a minute, just kidding. Never mind, I'm saying it backwards. This is a combination because we don't care about what order the fruit is in, okay? So it's a combination because if you were to give somebody a recipe for something like a fruit salad, you don't care about the order that the fruit's listed in, right? It's all the same. So that would be a true combination. Now here's the one I was trying to get into, what I was trying to talk about. Sorry, I got ahead of myself. So, you'll hear people call locks combination locks, right? That's actually incorrect. Anybody know why that's incorrect to call it a combination lock?
Because
Good.
the order does matter.
The order does matter that you put in a combination lock, which actually really makes it a
lock, permutation.
A permutation lock, right. So that's where I was trying to get at. I was just getting ahead of myself there. So combination locks are actually permutation locks because the order does matter that we talk about. So when we talk about combination, order does not matter. And when we talk about permutation, order does matter. So here's something that always helped me to understand this. When I give the number of permutations, it's always going to be a larger number than the number of combinations. Anybody know why? Yeah, you have to divide for the combinations, and that's because for permutations, I'm counting not only the amount of things I can choose, but also the way I can position them, which means that I'm going to end up with more in the end, right? I'm going to have more types of situations if I'm talking about order as well. Like for example, if I have 3 students in the class, and I pick 3 students out of the bunch, if I don't care about the order of those students, I only have one choice. But if I then care about which order they're in, I have more choice. I have 6 choices, right? I can order 3 people in. So that's the difference. Keep in mind permutation amounts will be larger. So we have mathematical ways to actually do these things without actually sitting there and writing it all out. We have formulas for this. And the first thing we'll talk about is what we call a factorial in math, okay? So a factorial is a way that we can calculate product. So a factorial, for example, looks like an exclamation point. So if I say 4 factorial, what that means is 4 times 3 times 2 times 1. It's multiplying everything that is beyond, like right after that number. It's multiplying them together. And calculators will have an option to do that. So I'm going to be using the Desmos calculator today, just because I know everybody will have access to it, just to keep it like, so everybody has access to it. And these are the formulas for permutation and combination. So NPR represents permutation. Say we have a group of 9 things and we're choosing 3 of them. N would be 9, R would be 3. And then combination, we have a group of 9 things, we're choosing 3 of them. N would be 9, R would be 3. And this is the formula. So to start, I'm going to write everything out by hand, and then I'm going to show you how to use a calculator. So, getting to know the calculator operations. So, 8 factorial is the same thing as 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. But we also have a calculator that can do this, which can be useful, because if it's something really big, you might not want to sit there and calculate everything, right? So that's why it's useful to have a calculator. Now, this is a calculator everybody has access to. You can do it on a phone or a computer. desmos.com/scientific. Everybody will have access to this on their phone. And if you have a hand calculator, that will also work as well. There is a button for it. It's 3, 7, and 8 if you have one of these. Second, for all of those are the 3 operations we're going to be using. So, I'm sorry, you have a question?
No, it's okay.
Okay. So if you type in 8 and then you go to the function option right here, see this little exclamation point? That will give you that calculation. 40,320. So I'm going to move that over so I can write it. I can't write on the same screen that the calculator is on, so 40,320. All right. So now we're going to do a combination. So what this means is we have a group of 7 things, and we're choosing 3 of them, and we don't care about the order. That's what that really, this formula really is saying. So the way we do that, by hand. Let's pretend we're just going to do it by hand. So the way we...
So we have to calculate 7 things, and wait, could you re-explain that?
Yeah, so you have 7 items, whatever it is. We don't know the situation behind this. And you're choosing 3 of them, and we don't care about the order. How many ways can we do that? That's what this really is just saying. I'm just trying to explain what it means.
Okay.
So the way we would do this by hand would be, this is your N, and this is your R. So it's always, for combination, I see it's combination because the letter C. It's 7 factorial over N minus R. I always make sure I have this right. What's N minus R? Good. 4 factorial times just R. What's R? 3. So that's how you would do it by hand. Okay? So I sometimes will do this by hand. So this is just 7 times 6 times 5 times 4 times 3 times 2 times 1 all over 4 factorial is 4 times 3 times 2 times 1, and 3 factorial is 3 times 2 times 1. Now the reason I sometimes will do this by hand is because then I can cancel stuff out. I can cancel out the 1s, this 2, the 3, and the 4s, which leaves me with 7 times 6 times 5 divided by 6, which is 35, I believe. So this comes out to be 35. So this is how you would do it by hand.
You did 7 times 6, but don't you need to multiply that by 5 though?
Yeah, 7 times 6 times 5 divided by...
Oh, okay. I thought you said 7 times 6 times 5 was 35.
No, then divide it by 6, which is the denominator.
Okay.
So here's how you do it in the Desmos calculator, and then I'll talk about how you do it in the scientific. So 7, choose 3. You type in, you go to the function, and you hit NCR, because that's the one I'm using. And then you type in 7, 3, and it will give you the same answer we just got, 35. Now, if you have one of these calculators, the TI-30, you would type in the N first in your calculator, so you just type in 7. You hit second, 8, and then you type in 3 equals, and you should get 35. So they're a little bit, the operations in the calculators are a little bit different, but this is how you do it with the Desmos, which you all have access to. So it's N, R. So is everybody good with that? Okay. So now we'll go ahead and try the next one. And this one is not a combination, it's a what? Permutation. So the formula for, basically what this means is we have 7 things. We're choosing 3 of them, but we care about the order. We care about the order. We're counting all the possible ways we can position them. So the way we do a permutation is it's n factorial, so whatever your n is factorial, over, and then the denominator is just n minus r. What's n minus r? 4 factorial. So that's just 7 times, oops, I forgot 6. 7 times 6 times 5 times 4 times 3 times 2 times 1, all over 4 times 3 times 2 times 1. We can cancel out all the 4s, 3s, and 2s. And that will ultimately leave you with, I think it's either 210 or 120, I forget. It's 210. So 210. And you could also have used Desmos to do this. So if I pull up Desmos, if I just change this to a P, it now does a permutation. Okay? So that's the permutation of NPR is with N being 7 and R being 3 is 120 or 210. So let's talk about why these are different. So why are there more permutations than combinations of the same choices?
They count the order.
Good. So these this is how many ways we can take those things, like how many ways we can pick 3 things out of a group of 7. This one is counting that, but also counting how many ways we can then position each order. So that's why the number is more. So does everybody feel good about the calculations?
How would you do that
In this calculator? So you would type in the number 7, your N, and then you'd hit second 9, and then type in your R, which is 3, equals. Do you get it?
So in both combination and permutation formulas, the end is factorial.
Yeah, see the formulas are actually written on the back of your notes down here if you need them.
Yeah, I was just looking at them. I was just double checking.
Yeah, the only difference between the two is for combination, we additionally divide by R factorial. Everything else is the same.
Okay, so for combination, it's N minus R, and then the factorial of that, and then the factorial of R.
Correct.
Okay.
So, how many baseball teams of 9 members can be formed from 14 players? So, first thing you need to keep in mind is the problem is not always going to come out and just tell you, this is a combination, this is a permutation. You have to use the context of the problem to figure this out. So, if I'm picking teams of 9 members from 14 players, do I care about the order?
No.
No, because once you have a team, we don't care about the order we picked the team, right? You're still all the same team. If I pick 9 people, it doesn't matter what order I pick them in. We still made the same team. So this is not a permutation, but it's a combination. So this would be 14 C9, which you can do in the calculator. 14 C9. Or you can do it by hand, and you should get 2002 combinations.
Okay, so for that one, we would do the what's it called? What's the exclamation point?
You're welcome. So this time you figured it out?
Yeah.
Okay, just checking.
How do you do it on the? Can you do it on the Apple?
It doesn't.
It doesn't?
As far as I know, it doesn't.
I'm doing it on my phone.
Oh well, he can teach you later then.
I can show you.
And
So, moving on. How many 9-player batter lineups can you create from a team of 18 baseball players? So in this case, is this a permutation or a combination? Good. Why is this a permutation? Good. And lineups order does matter, right? If I talk about like a batting lineup, the order matters. So this is a permutation. So this one's going to be 18 P9. So you can do it by hand or with the calculator.
you go back real quick. I just need to see the
Oh,
answer.
yeah, it's 2002.
2002.
Second, 9 equals, and you're going to get a really large number, 1.7643225 times 10 to the 10th. Have you seen it written in exponential before when the calculator gives you a big number? It can't fit. So how you would actually get the number is to then move the decimal place 10 digits to the right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then fill in the gaps with zeros. So that's 1, 7, 6, 4, 3, 2, 2, 5, 6, 0, 0. I put in my commas. And that's 17,643,225,600. Yeah, it's a big number. So do we have any questions about that one so far? Would you have thought there was like 17 billion ways to do that? No, it's crazy, right? So does anybody have any questions so far? Is everybody good? Okay. So now we're going to talk about combinations, permutations, and what we call special cases. I thought we had 2 more. Okay. So this is a really common question you'll be asked with this. How many ways can you arrange the letters in the word orange? Okay. So the first thing you always want to do when they ask you about arranging letters in a word is look through and see, do any of these letters in this word repeat? No. So in this case, you can either do it like this. So you have 6 choices for letters, right? You have 6 digits. And the first choice, you have how many options? 6 choices. Then we have 5, 4, 3, 2, and 1 left. We'd multiply them. And how else could I represent this now that you just learned a new way to represent this? 6.
Would it be 6, C?
No.
Oh, so 6P and then...
It's just 6 exclamation point, right? Because 6 factorial is just 6 times 5 times 4 times 3 times 2 times 1.
I was thinking like, since it was a specific amount of letters, that'd be P.
No, so in this case, it's just, you could do 6 choose 6, yeah, but this is just 6 factorial. I'm just showing you, if you write something times like all of its predecessors, you can just write it as 6 factorial.
And you saying we could do 6, what 6? Like...
Don't even worry about that, that's just too
Okay.
complicated. So that's just 720. Now, that's how you would do this calculation. You would have 720 ways to do that. So for the next one, this one's a little bit different. This is where you have to be a little more careful. We have the word trigonometry. First thing you want to do is count how many letters are in this word. 12. So the way we do this is however many letters you have to arrange, in this case 12 factorial, is going to be your numerator, okay? But we're going to have a denominator here because there are letters that do what? Repeat. So here's how you do that. You count the letters that repeat. So
It's 6.
well, yeah, we have to count each one individually. So how many times does T repeat?
2.
So it's going to be 2 factorial.
No, wait, individually.
So how many times does the letter O repeat? 2. 2 factorial. And any other letters repeat?
Yeah, R.
R. And how many times?
2.
2 factorial. So you divide it by however many letters repeat, the factorial of that. Now the easiest way to do this is 12 factorial over. Now let's think about what 2 factorial is. 2 factorial is 2 times what? 1. What's 2 times 1? 2. So this is just 2. What's 2 times 2 times 2? 8. So that's an easier way to type it in your calculator if you're wondering. And that is 598,75200. That's 59,875,200. Who would have thought that many ways, right? It seems always impossible to me every time I do it. But does anyone have any questions on that? So that's the procedure you use all the time. Now, say no letters repeat, you just don't have a denominator, okay? So this one, bear with me, this one's a little bit confusing, so make sure you're with me on this question. So we have a 5-digit whole number between 56,000 and 59,999, and how many of those can be formed if no digit repeats? So we have a 5-digit number. Let's write it out. So the number is between these two numbers, which we automatically know means that its 10,000th place number is going to be what? 5. So we have how many choices for that slot? Just one. We only have one choice for this slot. It's already determined for us. This slot is determined. It's going to be 50 something, right? Because it's between those two numbers. Now, we know that the next digit right here is going to be between, you're almost there. So it's going to be, it's going to fall between these two numbers total. So it's either going to be a 6, a 7, an 8, or a 9, right?
Mm-hmm. So it'd be 4.
Yes, it would be 4. So basically, if we think of the numbers that are between 56,000 and 59,999, it would be all the numbers with 56 in the beginning, then we move on to 57 something, then 58, and then 59. So there's only 4 choices this number can be the thousands place.
So would the rest be 10?
No, watch. Be careful. That's a good point, but no, you can't be 10 because here we have 10 choices, but what's the problem? Here's the part I'll give you a hint. No digit is repeated. So there's not 10 choices there. There's how many? How many numbers did we already use up?
Would it be 100? Wait, no.
8.
Wait, so you only have to use single numbers then, right?
Yes. We're only talking about, we're doing each digit specifically its own. Each slot represents a single digit, meaning it can max be 10.
Okay.
So we already used up a digit here and a digit here, meaning there's only 8 free digits left. And these are also free because they're between 0 and 9. But the problem is we already used 3 digits. So how many are left for this slot?
7, 6.
And 6. Yeah, this problem is really.
Why did you do 8 for that first one?
So we already used a digit here.
Yeah.
We already used a digit here.
Mm-hmm.
We can't repeat any digits, meaning there's only 8 choices left.
Oh, and then you count down from there.
And then I count down from there because I've already used them. So this comes out to be 1,344.
It seems very easy to make a mistake. Like
It is.
If you make like one mistake, you die.
So yeah, it's actually a good point you're gonna make because when I took combinatorics in college, my professor, he was always like, you need to do the problem and then have your friend do the problem and then you do it together because this is one of those things you can really understand the concept, but it's very simple to just like overlook something. So you just really need to check your work on these. So does anybody have any questions about that one? I know that one's a little bit confusing. So let's try the next one. How many 4-digit numbers can be formed if the leading digit cannot be 0 and no repetition of digits is allowed? So we have 4 digits. So the first digit can be anything except for what?
0.
So how many choices do we have?
9.
Good.
Alright. Can I just go out of the limb here and take a guess?
Sure, go ahead.
9876.
Correct. So I'll explain why. So the reason it's that is because this one can't be 0, so we have 9 choices. This one, it can't be whatever this one is, but it can be anything else, so we have 9 choices. This one can be anything except for whatever the first 2 are, and this one can be anything except for whatever these 3 are. Does that make sense?
Mm-hmm.
So we multiply those together.
So the second one could be 0?
Yeah, the second one is okay to be 0, so it can be anything except for whatever the first one was, which leaves you 9 choices.
Wait, why'd you put 9987?
Cause the first one, it can't be 0, so you have 9 choices. The next one can be, 0.
It's
Yeah.
gonna be
Okay.
9.
The next one can be anything except for whatever the first one was.
Yes, you said.
Yeah. This topic's tricky, I'm not gonna lie.
Yeah, it's very easy, but it's also very easy to mess up.
Yes, it really is.
The
So-
answer was 4,536, right?
Correct. So this one says how many committees of 3 men and 3 women can be formed from a group of 10 men and 8 women. So
3 men and 3 women. Would that be 3? Would that be 2 slots of 3?
we actually can't use slots here because it would be too confusing. So there's actually a better way to do this one. So it says how many committees of 3 men and 3 women can be formed from a group of 10 men and 8 women. So the first thing I look at when I see this problem is we're grouping the committees by gender, right? So we don't care about, like, we're not mixing gender, so we can keep those as 2 separate calculations. So we're taking 10 men and we're choosing how many of them? Times, because we're also picking women. How many women do we have total?
8.
Good. 8C3. So if you do those calculations in the calculator, this one comes out to be 120 times 56, which is 6,720. So yeah, you're basically just choosing, and we don't care about order here. So that's why I did C instead of P. Everybody understand that? And we're multiplying them because we have to have, oh, thank you. I was like about to get up. So multiplication, the same principle for multiplication. See how there's an and right here? Just like it applies to probability. And means you multiply. Same with combinations. So the next one. How many ways can 5 movies be rented from 8 westerns and 12 sci-fi movies if you want at least, this is where it gets complicated, at least 2 westerners? So this one's a little bit tricky. So if you want at least 2 westerners, that means you're okay with 2, 3, 4, or 5 of them, right?
Yeah.
Being picked. So the first scenario, there's several different scenarios that can happen. Okay? You have 8 westerner movies, whatever they're called. I don't know. I've never seen one of those. And you choose 2 of them. Okay? Times you have 12 sci-fi movies, and you have to choose how many of those?
0.
3.
3.
Because it has to add up to 5, right?
Yeah.
So that's the first scenario that can happen. And then or, what operation do we use for or? Addition. Or, what else can happen is, we have 8 westerners, and we choose 3 of them. Because you can also have 3, because at least means you could have 3, 2 or more, right? Times. Then we have 12 sci-fi, and we choose how many of them? 2. Plus, or, what could also happen is we have 8, and we choose 4, times, good, 12 and we choose 1. Next one. We have 8 westerners and we choose how many of them? All 5. Meaning, we then have 12 sci-fi movies to choose from. We choose how many of them?
0.
0. It's a lot, yeah. Does it make sense when I explain it though?
Yeah, it makes sense, but
So
I
wait.
don't know right now.
If you're wondering, it comes out to be this. I did the math ahead of time. So this is a more complex version of this kind of problem. Basically what it's saying is you can have at least 2 westerners. So you're okay with having 2, 3, 4, or 5 of them. So whatever you choose for Westerners, remember the other part that you choose is sci-fi. Yeah, this is a harder problem. I probably wouldn't give you one like this to do on a test. This hard.
Thank the Lord.
Test, homework, yeah, there might be a few on there that are sort of like this. But do you understand it now that I explained it?
That makes sense. It's a lot of work.
Yeah. Okay, we got 2 more problems to do and then we'll be done. I know this is a lot. So, if you flip a fair coin 4 times, what is the probability that you get A, exactly 2 tails? Let's do that first. So, if you get exactly 2 tails, do I care which flips are tails? Do I care what order it's in? No, so it's not a permutation, it's a? Good. So we have 4 choose 2. But keep in mind, this is probability. Probabilities always have denominators. So let's talk about what the denominator is here. So if you flip a fair coin 4 times, okay, how many different options do you have for sequences? 2 to the what power? 4th power. So basically what that means is, I'll explain this more simply, that's 16. If you flip a fair coin 4 times, there's 16 combinations of things that can happen. You can get heads, 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 tails, 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 and so on. 16 ways. So this comes out to be 6 out of 16, which is 3/8. So that's part A. Now the next one is the probability of getting at least. When you see that at least, you know it's going to be a long problem. So, at least 2 tails. That means you're okay with getting 4 choose 2 tails. You're also okay with getting 4 choose 3 tails. And you're also okay with, what's the last situation you're okay with?
Good. 4 tails and nothing else.
Good, just 4 choose 4. All out of the same total, there's still 16 trials. Which comes out to be 11 out of 16.
So, what does the 4 stand for again? The 4 times you flip?
It means, yeah, the 4 times you flip. Exactly. The 4 trials.
So you'd be fine with getting 4 and 2 tails, and then 4 and then 3 tails, and then 4 and 4 tails?
Exactly. Yep, because you're okay with at least 2, meaning you want 2 or more.
Okay. But it just needs to be as much as the n, right?
Yes.
Okay.
At least means that or more than that. Oh, you're not done.
Yeah, I'm a little not quick.
That's okay.
Thank you.
You're welcome. Alright, the next one. Last one. I know this was kind of long. A teacher randomly picks 3 students from a class consisting of 6 boys and 4 girls. What is the probability that everyone is a boy? So, let's think of the situation that only boys are chosen. So, how many boys do we have to choose from?
6.
And how many of them are chosen? 3. Out of the chances of anybody being picked. So, what's the total number of students that we could have picked from?
10.
And we're choosing how many of them? 3. So that is 1/6. And there are sometimes situations in probability and combinations where there's different ways that it could have been done as well.
Did you hear out loud?
Yes.